All right. So we're going to start in on our next chapter here, and I've kind of lumped these two chapters together because they have the same focus here. So this is now chapters 22 and 23. And our focus here is going to be on what's called alpha carbon chemistry. All right. So our focus here is actually still going to be our aldehydes and ketones. Okay, and up until now, our focus on aldehydes and ketones have been on one specific carbon, one specific reactive site of these molecules here. And what was that? What carbon are we focused on in aldehydes and ketones? That carbonyl carbon. And why? What do we know about that carbonyl carbon? Electrophilic. Electrophilic carbonyl carbon. All right? So up until now, we've been focused on this carbonyl carbon and the fact that it is electrophilic. Can accept pairs of electrons. All right, but this chapter here is alpha carbon chemistry. All right, so if we start counting away from our carbonyl carbon, they've just labeled these with the letters of the Greek alphabet. So this over here, the next door neighbor to your carbonyl carbon, these are your alpha carbons. We could keep on going down the line. These next ones here are your beta carbons. Yeah, gamma carbons, epsilon carbons, etc., etc. All right, but our focus here is on these alpha carbons, all right, and chemistry that occurs at these alpha carbons. So up until now, everything that we've learned about aldehydes and ketones have been centered around that carbonyl carbon playing the role of the electrophile. Now we're going to learn about these next door neighbor carbons as well. They turn out to be pretty interesting. All right, and so the shtick here with these alpha carbons are weakly acidic. Okay, we can even kind of put in very weakly acidic, quite weakly acidic. All right. So by weakly acidic, by very weakly acidic, I don't mean that we take an aldehyde and ketone and we add it to water and all of a sudden the pH drops really significantly. We don't think about them as normal acids like we would hydrochloric acid or even like acetic acid, another weak acid, right? These very weakly acidic alpha carbons, the bottom line here is they can be deprotonated. So if we have a base strong enough, we can actually remove a hydrogen from that alpha carbon. All right, so why is this a big deal? So let's kind of remind ourselves, we have this measure of acidity that we can use, which are called pKa values. And so we're going to compare the pKa's of a bunch of different carbons. All right, we talked about pKa's all the way at the beginning of the last semester, our first semester, as a way to measure acidity. So let's just remind ourselves, something like acetic acid has a pKa of 4.8, whereas something like hydrobromic acid has a pKa of -10. Again, our pKa's here are measures of our acid strength. So what's a stronger acid? A large pKa value or a small pKa value? A small pKa value. All right, so just to kind of use examples that we should have some intuitive sense of. All right, the smaller the pKa value, that implies a stronger acid. Okay, so we're going to make a little chart here where we're going to list things from the most acidic to the least acidic. And we'll compare them with their pKa values here. All right. So just kind of a good benchmark to throw down here first would be water. Water is not something that we think about as an acid. We're not worried about spilling water on ourselves. What are we going to do? Wash it off with more water? All right. So we're not worried about that being an acid in the sense of a corrosive acid. But nonetheless, it can play the role of a proton donor. It's got a pKa of around 16. All right, our ketone, specifically the alpha carbon of that ketone, all right, this has a pKa of around 20. So are ketones stronger acids than water? No, they're weaker, right? So it's even harder to remove a proton from a ketone than it is from water. But nonetheless, this is not some astronomically huge value here, right? This is still doable. A pKa of 20 means that we can indeed get a base strong enough to do it. All right. As an example, ammonia, NH3, this is even harder to remove a proton from. This has a pKa of 36. All right, so it's easier to remove a hydrogen from an alpha carbon than it is from even a nitrogen. Right? And to put this into perspective here, okay, a typical alkane carbon. So now if instead of looking at acetone, I look at propane, where I'm again removing a hydrogen from a carbon atom, this has a pKa of around 60. Which basically means it's impossible to remove a proton from an alkane. So most carbons hold on to their hydrogens very, very tightly. It's very difficult to deprotonate a regular old carbon. But if we put that carbon right next to this carbonyl group here, all of a sudden we see this much more reasonable pKa value here. We can actually get a base that could effectively remove that hydrogen from a carbonyl carbon, or from the alpha carbon. And if instead we take that alpha carbon and we sandwich it between not one but two carbonyl groups, all of a sudden that pKa value drops significantly to around 9. A very easy to remove hydrogen, right? So those carbonyl groups being right next door to that alpha carbon make it much easier to remove a hydrogen from that alpha carbon, right? There's only one, like in a ketone, we have a pKa around 20. If we have two of them, all of a sudden our pKa is significantly less than water, around 9. All right, so then why? All right, why are those alpha carbons relatively acidic? All right, well, in order to do this, we're going to have to look at our conjugate base. So we're going to do an acid-base reaction here. I'm going to take my ketone. I'm going to draw that alpha carbon hydrogen bond specifically. And I'm going to mix it in with some base like sodium hydroxide. And everybody's going to take a second and give me my acid-base reaction here. What would my products be from this acid-base reaction? bases the nucleophile, attacks that electrophilic acidic hydrogen, and that pair of electrons jumps onto that carbon there, creating my conjugate base here with that negative charge on that carbon and water. All right, if we're going to be good with our arrow here, we learned how to do this back in the first semester. We can predict the direction of our equilibrium by looking at the pKa of our acid and our conjugate acid. This has a pKa value of 20, whereas this has a pKa value of 16. The stronger acid wins, so this reaction does favor our reactants here, but not all that strongly. All right, we still get some product that forms here. And even if there's only 0.1% of this guy floating around in solution, it turns out to be really important for the chemistry of those carbons, all right? Because this carbon here with its negative charge could play the role of what in a reaction? Nucleophile or electrophile? A nucleophile. Now we have this net negative charge here. So in our aldehydes and ketones, we have this carbonyl carbon that can play the role of an electrophile. But under certain conditions, we have our alpha carbon that can play the role of a nucleophile. All right, so that's what's going to make our aldehydes and ketones a very interesting functional group. A functional group that we've split over multiple chapters here. Because in the first instance, we were talking about that electrophilic site, and now we're talking about this alpha carbon, this new nucleophilic site. And it's a nucleophile because it's weakly acidic. We can deprotonate it, giving it that negative charge. All right, we still haven't really answered, though, why this is relatively acidic. So let's take this conjugate base here, and let's note that this is not our only form of our conjugate base. This has that allylic lone pair, which was one of our resonance patterns. All right, and so we can draw this other resonance contributor here. Okay, I'm going to draw our other resonance contributor, and you're going to fill in the missing electron pushing arrows. Right, we have this pair of electrons coming to form our carbon-carbon double bond and kicking up this pair of electrons. So we have these two resonance structures that we can draw. So why is that alpha carbon relatively acidic? Because that negative charge can be stabilized through resonance. It can be passed on to that even more electronegative oxygen atom. All right, so first of all, we got a name for this thing here. And again, since this is in resonance, we got to think about both of them together when we're thinking about our molecule. It's not one of these that is true, but both of them that are true at the same time. So this whole thing is called the enolate ion. All right, and what we've shown is that that negative charge is being stabilized through resonance. All All right, so why is that alpha carbon relatively acidic? Well, because when we deprotonate that alpha carbon, we give that alpha carbon a negative charge, just like we do for every acid that we deprotonate. But now that negative charge can be passed up to that oxygen atom, stabilized through resonance. All right, so that's why these aldehydes and ketones are more acidic than, say, regular old alkanes. All right, and as we noted, that alpha carbon can play the role of a nucleophile in a reaction. All right. Cool. So before we start talking about aldehyde, or rather that role of that alpha carbon as a nucleophile, we're going to have to remind everybody of another time that we've seen this similar thing when we were talking about ketoenol tautomerizations. All right, a tautomerization is a fancy way of saying an internal rearrangement of atoms. Okay, it turns out that that ketone is always in an equilibrium. Granted, an equilibrium that favors that ketone form, but it is nonetheless in an equilibrium with what's called an enol, where we have that carbon-carbon double bond located right next to an alcohol group. I'm going to be good and show this OH bond here to make a point. All right, because we're going to do our reaction mechanism here for this tautomerization. And the first step is I want you to identify all the bonds that we need to break over here on the left and all the new bonds we need to form over here on the right in order for this reaction to occur. All right, what bonds do I need to break? Who's got a bond to break for me? Which one? The carbon-oxygen double bond. Yeah, I'm going to need to break one of those. Break my pi bond. All right. What about forming? So I need this bond here. What else do I need? Carbon-carbon double bond. All right, we're missing one bond to break here. We got one additional bond that we're going to have to break in order for this reaction to occur. I want everybody to take a second and put in your implied hydrogens and see if you can't figure out what bond we need to break in order to get from our reactant side to our product side here. Has anybody got it? So we have on our alpha carbon on the left, we have 3 hydrogens. And after we form our enol, how many hydrogens do I have? Just 2. So yes, I'm going to have to break that carbon-hydrogen bond as well. All right? That's why you can convince yourselves that this molecule has the same chemical formula as this molecule. I didn't add any new atoms in there. All I did was do this internal rearrangement. Cool. All right, so this reaction here can be catalyzed under either acidic or basic conditions. We're going to do together the reaction mechanism under acidic conditions. Okay. Let me get rid of all my little markings here. I'm actually going to move my double bond to the other side just because it's going to be easier to draw. Okay, so if we're under acidic conditions here, let's put in a proton donor like hydronium. Okay, what's going to be the first step here in our mechanism? Under acidic conditions with these oxygens, we saw this when we were talking about our nucleophilic addition to aldehydes and ketones. We saw this when we were talking about alcohols as well. Our first step here is going to be to protonate that oxygen. Right, so we've generated that water molecule, that leaving group from our electrophilic hydronium ion. And now we have this protonated ketone here. All right, so how are we going to get to our enol product? I want everybody to take a second. See if you can't get to that enol product there. All right, so if you were like, well, this is a nucleophile, a weak nucleophile, here's an electrophile, so let's do this nucleophilic attack here. Great, that is definitely something that does occur. All right, but again, we're not focused on that electrophilic carbonyl carbon. We're focused on that alpha carbon. That would get you a gem diol, but that's not what we're talking about here. We're talking about this alpha carbon. And as we said, we need to break that carbon-hydrogen bond. That'll allow that pair of electrons to form my carbon-carbon double bond. And finally, that enol product. Right? I guess I didn't lay it out. So this keto-enol tautomerization, because this is a ketone, and this thing over here is what we call an enol. So that means that there are now two reactions that we learned about that occur under acidic aqueous conditions here. All right, so let's just note, we have our ketones and aldehydes in an aqueous solution. All right. we learned about how they will react with this aqueous solution to form a gem diol, where we have those two, a gem diol, a twin diol here, where we have those two OH groups on the same carbon. All right, this exists in this equilibrium that very much so favors our, whoop, not that direction actually, my bad. Other direction. Favors our ketone product, or our ketone. Nonetheless, this reaction is always occurring in an aqueous solution. You can use that to demonstrate that your oxygen is being exchanged with your solvent pretty easily. All right, but this would be a result of that nucleophilic attack of that electrophilic carbonyl carbon. And it turns out that this gem diol that you form here is pretty boring. It itself does not go on and do any other reactions. And since this equilibrium lies pretty strongly in favor of our ketone here, yes, this is always going back and forth, but there's not anything interesting that will happen with that gem diol. The other thing that's always happening in solution is, again, an equilibrium that strongly favors that ketone, but forming an enol. And this is a result of that tautomerization at that alpha carbon, so at that other reactive carbon that we're introducing this chapter. And unlike our gem diol that's pretty boring, it turns out that this enol here can be a nucleophile. All right, specifically at that carbon-carbon bond, just like we've seen with alkenes playing the role of nucleophiles, our enol's carbon-carbon bond can also be a nucleophile, a pair of electrons that can be donated. So in aqueous solution, ketones and aldehydes, they're always bouncing back and forth between these various forms. We talked last class, rather last chapter, about these gem diols that form, but these gem diols are pretty boring. All right, now we're talking about this other form here, these enols, and they're a little bit more interesting because these enols can be nucleophiles. All right, so let's do an example of a reaction where that enol is playing the role of a nucleophile. It's what's called alpha carbon halogenation. All right, and we're going to take this topic of alpha carbon halogenation and we're going to break it down into like 3 little subcategories here, depending on our conditions. So the first one is going to be what occurs under acidic conditions. All right, so first of all, what do we mean by alpha carbon halogenation? Let's take a ketone. We're going to put it in the presence of a halogen under acidic conditions. And we are going to halogenate that alpha carbon. All right, so how does this occur? Okay, we won't do the full mechanism since we just did it, but everybody's going to take a second and draw me that enol that we know is in equilibrium with our ketone under these acidic conditions. And as we said, that enol can be a nucleophile. So now, oops, I need a lone pair up here. So now let's put this in the presence of our electrophile, that halogen. All right, and what do nucleophiles do to electrophiles? They attack. All right, so let's do our nucleophilic attack. Kick off that leaving group. All right, but if I use that double bond and do that bond breaking and formation arrow, what else am I going to have to include in my intermediate here? A carbocation. All right, now, this is not what forms here. Because remember, we talked about what's wrong with carbocations. Why are they so much less stable than other things with positive formal charges? How many bonds does my carbon have in a carbocation? How many bonds do I have here? 3. So how many electrons are in that octet? Holy hell. There are 3 bonds. How many electrons are in the octet if each bond is a pair of electrons? 6. So because we have an incomplete octet, carbocations are less stable. So we can make this more stable if this pair of electrons comes down at the same time. Then my formal charge isn't on a carbon with its incomplete octet, but it's on this oxygen with a complete octet. We played this game in our last chapter as well, trying to avoid those carbocation intermediates, right? Because they have incomplete octets, so they're less stable than, say, this positively charged oxygen. All right, so then we have one more step to go here. We have to deprotonate our carbonyl oxygen. We need some base to do it here. In this solution, we have bromide ions and water molecules. Which one is going to be playing the role of the base here? Bromides are super duper stable, which is why hydrobromic acid is such a strong acid, because this thing does not want a proton, right? That's why hydrobromic acid has a pKa of -10 compared to like 0 for hydronium. So water is actually a stronger base. Truthfully, depending on the text, you'll see both of these, but if we're being really correct here and using our proper base, it would be water that would be playing the role of the base, creating our hydronium ions, right? So rather than HBr being produced in aqueous solution, it's more correct to say it's hydronium and bromide that are produced in aqueous solution. All right, but we've halogenated that alpha carbon. All right, so we used this symmetric ketone acetone. What if we used an asymmetric ketone? So now let's take a ketone. But we're going to put 2 other methyl groups over here, make it asymmetric. We're going to do the same conditions here, bromine under acidic conditions. But now we've got these two separate alpha carbons. So we would get a different product if we brominated the alpha carbon on the left than we would if we brominated our alpha carbon on our right. All right, and I'm going to tell you that only one of these two products form. And I want you to try to figure it out by drawing our enol intermediates that would lead to either one of these carbons, either one of these products here. So what enol would I use to form the product on the left? What enol would I use to form the product on the right? Right? If I'm going to form my products where that halogen is over on that leftmost alpha carbon, that means that my carbon-carbon double bond in my enol had to form on that leftmost carbon. And if I'm going to do my product where my enol forms on that rightmost carbon, that means that my enol has to have its carbon-carbon double bond over on the right. All right, and as I said, only one of these two products will actually form. And that's because one of these enols is more stable than the other one. So I want you to take a look at these two enols carefully and determine which one is going to be more stable, the one on the left or the one on the right. Why the one on the right? What is it? Substituted, right? More substituted carbon-carbon double bond here. So this enol here, more stable because it's more substituted. All right, so this will lead to my major product for our reaction here. All right, so if we have an asymmetric ketone, we're going to have to think about which one of our enol intermediates is more stable, which one is more substituted. That will lead to our major product for that reaction. All right, so we broke this up into alpha carbon halogenation under acidic conditions. We talked about when we have this asymmetric ketone. What about under basic conditions? Right? Under basic conditions, we can deprotonate that alpha hydrogen, that alpha carbon's hydrogen, leading to that enolate ion, which is an even better nucleophile than our enol. How could I tell that this thing here is an even better nucleophile than just my regular old enol, my neutral enol? It's the dead giveaway for a good nucleophile. That negative charge. So under basic conditions, we form those enolate ions. If I was being good, I would show both of my resonance contributors here. Kind of being lazy and just showing one of them. All right, but we get this even stronger nucleophile, even better nucleophile. All right, so if we take our ketone, and we put it in the presence of our halogen under basic conditions, we will brominate, halogenate that alpha carbon. All right, but since that first step is removing that alpha hydrogen with that base, when we add a halogen to that alpha carbon here, we have made it even more acidic. So what does that mean about the other hydrogen on there? Is it going to be harder to remove or easier to remove? It's even easier to remove because now that carbon is even more acidic. So what you're going to get is not just one reaction, but it's going to react under basic conditions over and over and over again until you fully halogenate those alpha carbons. Right, so under basic conditions, we're going to replace all of our alpha hydrogens with halogens. Right? Under acidic conditions, we get this monohalogenated product, only a single halogen on our alpha carbon. Because of that, we got to worry about our substitution if we have an asymmetric aldehyde or ketone. Under basic conditions, we don't have to worry about any of that jazz because we're just going to replace every single one of our alpha hydrogens with a halogen, right? That's because after that first halogenation event, all we've done is made that alpha carbon an even better acid. So it's just going to happen over and over and over again, replacing all of those alpha hydrogens. Okay, the one exception here, the one special case, is if we have a methyl ketone under basic conditions. All right, so first of all, by a methyl ketone, I mean a ketone where one of those alkyl groups bonded to that carbonyl carbon is a methyl group. So on one side, I just got the one carbon. Okay. If we treat this with bromine in the presence of a base, all right, again, we get bromination of our alpha carbon that then happens over and over and over again, because as soon as we brominate it the first time, it is that much more reactive going forward. And because this methyl carbon is the one that's the most accessible, that's the one that gets deprotonated first. Okay, so we quickly create this fully brominated methyl carbon here. Okay, we can note in this first step here, we fully brominate the more accessible methyl carbon. All right, but we've talked about these carbons with these 3 halogens, these fully brominated carbons here. These are good. They're strong electron withdrawing groups, and importantly for this case here, good leaving groups. So before this other alpha carbon even has a chance of being deprotonated, my hydroxide, which is both a good base but also a good nucleophile, is going to attack that carbonyl carbon. This creates our intermediate here. We've seen this intermediate a bunch, so much so that we gave it a special name, named after its geometry. All right, what was that name? Our carbon goes from being trigonal planar to tetrahedral, so we called this a tetrahedral intermediate. And previously, every time we saw these tetrahedral intermediates, it was stuck here. All right, it was stuck here, and we just had to protonate that oxygen. In this case, because we have a good leaving group, it's not stuck. That pair of electrons is going to come back down and kick off that leaving group. And so instead of creating a brominated product here, we brominated that methyl carbon and then kicked it off, creating a carboxylic acid. All right, so in the case of a methyl ketone under basic conditions, we're going to create a carboxylic acid product. All right, your other alpha carbon here does not get brominated at all because, again, the methyl carbon gets brominated first because it's more accessible. And then as soon as you create this carboxylic acid, this is no longer going to be the acidic site in this molecule. This carboxylic acid hydrogen is, right? So this is the one that's going to be removed under basic conditions. You won't have any more reaction at that alpha carbon. So instead of getting a brominated alpha carbon, you create a carboxylic acid. Cool. All right, again, no class on Friday. Work on your chemistry and careers project, get your interview questions done, and we'll pick up with this stuff on Monday of next week.